do the following. What does Bernstein's theorem say? For two binomials. Let's say my first equation is x to the a1, y to the b1, minus c1. These are constants. And my second equation is x to the a2, y to the b2, minus c2. Now I can, without loss of generality, assume that there's a constant term, because if there's a monomial factor, I just remove it, right? And I will also allow, maybe for now, ai and bi are non-negative integers, but we'll see in a moment they could be integers. And let's say ci is non-zero constant number. So what does Bernstein's theorem say? Okay. Well, we should calculate the Newton polygons, and then we should take the Minkowski sum, the mixed area of the two Newton polygons. So let's color code this. So here we have G, and here we have H. So G, the Newton polygon, is just a line segment in the plane. Right? It's just a line segment in the plane. The Newton polygon of H, Newton polytope, is another line segment in the plane. So we need to calculate the mixed area of two line segments in the plane. Okay? So what's the mixed area? Well, that's the area of the sum minus the red area minus the blue area. But the red area is 0 and the blue area is 0. Right? So therefore, the mixed area is simply the area of the parallelogram. The area of the parallelogram, which is the determinant of the coefficient matrix. Okay, so Bernstein's theorem, and this says that the number of common solutions, the expected number of common solutions, if the C1 and C2 are random, in this case a non-zero is enough, is just the absolute value of A1, B1, A2, B2, and that's it, right? So this is Bernstein's theorem. So what we saw on the first exercise sheet, homework number 1, that the number of solutions to a system of n binomials in n equations is just the determinant of the exponent matrix. That's a very special case, and I would like to prove this for you. So I'd like to actually outline for you a proof, and this is going to be a lemma. Okay? So the goal is I'd like to show you a proof of Bernstein's algorithm. So I'd like to tell you a proof. But by proof, I really mean a constructive proof. There are many proofs of Bernstein's theorem. There are many ways to prove Bernstein's theorem. Okay? I like to give you an algorithm. I'd like to describe to you an algorithm that takes a system of sparse equations, G and H in general, solves these systems in a way that obviously shows that the number of solutions is the mixed area. Okay, that's the goal. Okay, so I want to give you an algorithm that constructs explicitly, numerically, mixed area, many solutions. And the way we're going to do that, we're going to reduce it to the case of binomial systems. So I'm going to build a subroutine for solving binomial systems, and then the general case, we'll call that subroutine. Is that clear? So I'd like to show you how to solve a system of two polynomials and two variables, G and H, which constructs mixed area many solutions, and as a subroutine, we're going to call the binomial subroutine. You look puzzled. Okay? So that's the goal. Okay? So that's how does the binomial subroutine work? Well, we need to do a little bit of integer linear algebra. So, for example, we can use the Hermite normal form from integer linear algebra. So, in that we compute an invertible matrix Uij, which is an invertible 2 by 2 integer matrix. So it's an integer matrix with determinant +1 or -1, such that U11, U12, U21, U22 times the given exponent matrix B2 is an upper triangular form. R1, R3, 0, R2. Okay? So this is called the Hermite normal form. So somebody referred to this 2 weeks ago as the Euclidean algorithm. This is really the Euclidean algorithm, and this is done by elementary row operations. So by the Euclidean algorithm here on the left column, by elementary row operations, I can take my integer matrix. I have an invertible integer matrix. Determinant is +1 or -1, and I can get it to this form. Okay? Now, of course, here the determinant is very easy, right? That's just R1 times R2, because it's an upper triangular matrix. Okay? So if you believe the Hermite normal form, I need to prove to you now that the number of solutions is R1 times R2. Okay, so let's do that. So here's the derivation. Okay, so, well, let's look at our equations. X to the A1, y to the B1 is equal to C1, and x to the A2, y to the B2 is equal to C2. Okay? Now I claim, let's do the following. So let's take the rows of our transformation matrix and perform operations. So I take this equation and I take the equation to the power U11. Here I take the equation to the power U12 and I multiply the equations. Left-hand side times left-hand side equals right-hand side times right-hand side. So let's do this carefully. So I'm going to get x A1 y to the B1 to the power U11, x to the A2 y to the B2, U12 is equal to C1, U11, C2, U22. And for the second one, 1, 2. And for the second one, I take the second row of the transformation matrix. So x to the A1, y to the B1, U21, x to the A2, y2, U22 is C1, U21, C2, U22. Now clearly the forward direction holds, right? The forward direction holds for any matrix U, for any integer matrix U, because x and y are non-zero numbers. X and y are non-zero, unknown, non-zero complex numbers. The forward direction always holds. The backwards direction holds because the matrix is invertible, right? So U is invertible over the integers. So the backwards direction also holds, right? Because if I have any solution x, y to this system, by the same argument with the inverse matrix, I go back. So they are equivalent, okay? But now, this is equivalent to, well, let's look what's happening. Let's collect terms. So x to the A1, U11, plus A2, U12. That's R1. So this one here is x to the R1 y to the R2 is equal to C1 U11 C2 U12. Right? I'm just rewriting the left-hand side according to this equation, the first row. Now watch this. Now we're going to use the second row. Okay, so then in the second row we get y to the R2 is C1 to the U21 C2 to the U22. That's probably true. That's a 3. So R1, R2, R3. And here it's correct. Okay? So because of this 0, right, this 0 says that this times this plus this times this is 0. So therefore there's no more x, right? But now, I mean, it's clear, right? So now this equation has R2 distinct reduced solutions over the complex numbers. For each of these solutions we get R1 values of x, and we get, you know, that's the proof. So
how do you know that the R1, R2, R3 are all non-negative?
They're not. They're not. But I'll take the absolute value. That's a very good question. So now, since you asked the question, I'm going to allow integer exponents. I'm going to work with Laurent polynomials. So my algorithm works with Laurent polynomials. But even if they're negative, I'm still okay. So suppose R2 is a negative number. Then this still has absolute value of R2 solutions. Here R2 can be negative, and here R1 could be positive or negative. So they can be negative. Okay, that's the binomial subroutine. So the binomial subroutine calls the Hermite normal form and then extracts roots of unity over there. Okay? That's the binomial subroutine. Is that clear? So maybe a good way to think about this, maybe you should think about this like a shape lemma for binomial systems. It's kind of like a multiplicative shape lemma. Right? So we saw the shape lemma for Gröbner bases in the zero-dimensional case that said we have a particular triangular form. It's a little bit like a shape lemma. It's like a multiplicative version of a shape lemma. And of course, you know, important, I mean, this works in any dimension. Right, so if you have n binomials and n variables, here you have an element in SLN. And this is the solution to problem 4 on the first homework sheet. Okay, that's the binomial subroutine. Okay, so now how we're going to organize our proof, how we're going to organize our algorithm in general. And here's what we do. Next topic, 3.3, is introducing a toric deformation. Okay, here's what we're going to do. Let's look at our original system in x and y. And I'm going to illustrate this for my original system. Okay. So the idea now is we want to, let me say this clearly. Okay, so the goal now, reduce the proof and algorithm, very important, the algorithm for Bernstein's theorem to binomial systems. That's the goal. Okay? So let's take our first equation. So the first equation was a1 plus a2x plus a3xy plus a4y. That was the first equation. And then we had b1 plus b2 x squared y plus b3 xy squared. So this is the problem we want to solve. So think for a moment that the a's and b's are random numbers. They're given to us. We want to solve this. Okay? So somebody tells us that this has 4 solutions. Jose says this has 4 solutions, right? Maybe we believe Jose. Maybe we don't believe Jose. Okay? Now we want to actually build those 4 solutions. So we want to, along the way, we want to prove it and find them. Right? We have every reason to believe you, but it's always good to check. Okay? So when we introduce a toric deformation, we introduce a new parameter t. So I'm going to introduce a parameter t. I'm going to write t to the new 1, t to the new 2, t to the new 3, t to the new 4. So I'm just multiplying each term by a different power of t. And here I'm introducing t to the omega 1, t to the omega 2, t to the omega 3. So I'm just multiplying this by some powers of t. Okay? Now what are these nus and the omegas? Well, we want them to be nu I and omega j to be sufficiently generic. Okay, so I want them, so let them be random. Okay, so they're integers, sufficiently generic integers. So the precise definition is, if you read along, is on page 35 of the notes, and I'll explain the precise definition. But for now, just think about them as random. I picked 7 integers, okay, like 11, 3, 5, minus 8, 9, 17, and minus 27. Okay, that's my choice. They'll be sufficiently generic. Okay? Now the zeros. So I don't know how many zeros there are, but whatever they are, every zero now will depend on a parameter. Right? Every zero will be depending on a parameter. So now for every value of t I can solve this. Right? There'll be some solution, and by the implicit function theorem or something, analytic continuation, I will have a certain number of roots, maybe 4, that depend on the parameter t. Okay? So what I'm getting is an algebraic function. And I want to count the number of branches. Right? So I have a certain number of solutions, and I'm interested in how many branches does this algebraic function has. Okay, so that's somehow the goal. So Matt explained that last week. That's exactly what Bertini does. So in numerical algebraic geometry, we have a system of equations. We want to solve this for t equals 1. That's our goal. We want to solve this for t equals 1. But maybe that's a hard problem. Maybe it's hard to solve it for t equals 1, but maybe there's some other value of t where that's easy to solve, right? Then we move the value of t, we solve it for some easy value of t, and then numerically we track to t equals 1. Right? That's numerical algebraic geometry. Okay? So that's the idea. So which value of t should we choose? Well, before I tell you, I mean, there are two ways to think about this, right? There are two different ways, fundamentally different ways to think about this. Either you can think about this as a zero-dimensional system that depends on a parameter t. Or you think about this as a curve in 3 space, right? You can also think about x, y, and t as being coordinates in 3-dimensional space, and this is a curve. This defines a curve in 3 space. Of course, that depends on mu, nu, and so on, but well, after we made the choice, this defines a curve in 3-dimensional space. Okay? And this is somehow, you know, a local parameterization of this curve. What value of t should we choose? Well, we're going to analyze this near the origin. So somehow we want to say, you know, may we understand what's happening for t close to 0. And then we hope to go back. Okay? Now suppose all the nu's and w's are positive integers. Then this is identically 0. Right? For t equals 0, we see z0 equals 0. Right? But maybe some of the exponents are negative. Then this is undefined. Right? So we have to make sense out of this. We really need to do some analysis. We can't just naively, you know, set t equals 0. That's not going to work. We have to analyze this for t equals 0. Okay? So somehow the idea is, we want to say x of t is x0, t to the nu, plus higher terms, higher order terms in t. And y of t is y of 0, t to the v, plus higher order terms. Somehow that's our idea, higher order terms in t, where in our analysis here x0 and y0 are non-zero complex numbers and u and v are rational numbers. So I claim that this is the kind of structure we're looking for. We're looking for a series that starts with some lowest power in t and then has some higher order stuff where the coefficients are complex numbers. So that's the goal. Now let's understand in the bigger picture what we're doing here. Okay, so today we're going to think about t as t. We're going to think about a deformation parameter t, and I'm going to speak for a moment. In a moment, I'm going to speak about the field of Puiseux series, certain algebraically closed field that we're going to use to make this precise. Okay, that's for undergraduate students. We're going to work over this field. Okay? But of course for kids, high school students, they think about calculus. Think about t as epsilon. Epsilon like in calculus, right? High school students study calculus. 110% of Korean high school students take the calculus BC test. I'm exaggerating. But of course, you know, they're all smart kids. All KAIST students in high school took calculus. And for them, t is epsilon. Just think about t as a small epsilon, right? T is epsilon. And you analyze this, you know, what happens when epsilon goes to 0, right? And there's a rule, you know, I forgot this now. This is L'Hopital's rule, right? So in calculus, you know, kids, right, they learn about L'Hopital's rule, you know, L'Hopital's rule. Yeah, so L'Hopital's rule says, you know, Well, maybe when epsilon goes to 0, bad things happen, but then you divide by appropriate power, you take some derivatives, and things are going to be okay. Right? That's what L'Hopital's rule says. So today, for advanced undergraduates, we're going to speak about this field. High school students, that's the level of the lunch talk tomorrow, think about t equals epsilon. Okay? Now, for numerical algebraic geometry, at the end of the day, we're going to talk about expansions into powers of 10 to the minus 1. That's what numerical analysis is all about. Numerical analysis is about computing with expansions into powers of 10 to the minus 1. But for adults, there's other fields, right? So for adults, for example, there's the field of p-adic numbers. Or in fact, any field with a valuation, any field with a non-Archimedean valuation will work. Okay, so if you're a graduate student or a postdoc, you can think about epsilon or t. If you're a combinatorialist or physicist, think about q. Q is the deformation parameter for physicists. But for adults, 2 p.m. lecture tomorrow, let's think about an arbitrary field with a valuation. Okay, it's all the same, really, from this point of view. Okay, so with that in mind, let's talk about Puiseux series. So question is, why does such a series expansion exist? Okay, why should such a series expansion exist? Okay, so the answer in the context of this lecture is, let's go back to pages 6 and 7 in the notes. So I skipped chapter 1 in the notes. I skipped chapter 1, but now I'm going to go back to chapter 1. I'm going to go back to section 1.4. So in the notes, there's a section 1.4 called Puiseux series. Okay, so let me talk about them. Is this clear? Any questions? We have a lot of time this morning. I still have 23.5 minutes. So you can interrupt me with questions. So I'm going to talk about Puiseux series now. So, okay, so let K be the field of rational numbers in T, and consider a polynomial in one variable. In K of x. Okay, so let's consider a polynomial P of T of x, AD T of plus plus A1 of T x plus A0 of T. So I'm going to look at a polynomial in one variable x of degree d with coefficients in the field of rational numbers, rational functions in T. Okay? This is a field that's a good field. We can compute it. We can email scalars. Okay? I can email you scalars in this field. You cannot email real numbers. But I can certainly email, scalars in this field. Okay, so let's look at a polynomial of degree d with coefficients in this field. Let me keep my toric deformation. Then we have Puiseux's theorem. 1.7. This polynomial P, let me call it, actually I don't like this notation. Let me write it P sub T of x. Okay? So it's a polynomial in x and somehow t is a parameter that's built into the field. So this equation, p of equals x, has these solutions. Counting multiplicities. In the appropriate field. Multiplicities in the field of Puiseux series. And that's the field C of t, which is the union over all positive integers, capital N, of C bracket bracket t to the 1 over n. Okay, what's that? These are Laurent, so if I write round bracket bracket, that's the field of Laurent series in this quantity. Okay, so these are power series with, in this variable, t to the 1 over n, with complex coefficients that start possibly at a negative exponent. So the Laurent series and t to the 1 over n. That's a field. Okay? But then I take larger and larger values of n. That together is an algebraically closed field called the field of Puiseux series. So Puiseux's theorem from the 18th century says that this is a field that's algebraically closed. It's an algebraically closed field. Well, then, of course, you know, it's an algebraically closed field. It contains this field. So note, there's a canonical inclusion of this field into this field. Right? So this is the field whose scalars I can email. This one I can't, right, because it contains the complex numbers. But certainly every rational function has a series expansion as a Laurent series, and then therefore it has an expansion as a Puiseux series. Okay, so clear? Right, so you have any rational function in t, then you can make a, let's make this a bit more interesting, right? So you can expand this as a power series, right? So okay, so I have an inclusion. Okay. Is this clear? So this is the field of Puiseux series. It's an algebraically closed field, and that's our field of scalars, and a polynomial in one variable has d roots in this algebraically closed field. Now, I don't know how many of you have practiced with this field. You know, it's a little bit like this. Arithmetic requires practice, right? So like skateboarding requires practice. If you've never skateboarded before or skied or bicycled, that's a difficult thing, right? That requires practice. The same with arithmetic, right? Long division is hard, right? But you know, the only reason we're good at it is at age, I don't know, when people in Korea learn long division, but you practice, and after school long division, and eventually become good at it. And the same with Puiseux series expansion, right? So it requires a little bit of practice. So this afternoon, we're going to practice a little bit of arithmetic with this field. It's a nice field. It has characteristic 0, but you know, it has residue characteristic 0. But of course, the understanding is, you know, this is a placeholder for more general situations also. Okay, so what about Puiseux series? Do they converge? Here are some questions. Do these series actually converge? What is K bar? Well, that's K, right? What's K bar? How to compute these series solutions? How do you actually do this? How to compute these series solutions? Right, so I give you a polynomial in one variable with coefficients in here. How do you actually compute this? Okay. So series solutions, I have this form. X to the t is equal to x to the 0, t to the u, plus higher order terms in t. How do you do this? That's a problem of numerical analysis, right? That's a numerical analysis problem. Right? We're computing an expansion, bunch of terms, as accurately as possible into powers of t. Usually we do powers of 10 to the minus 1. Occasionally we do powers of p. Right? But that's a numerical analysis, that's a problem of numerical algebraic geometry. How do you actually do this? How do you achieve a certain accuracy? So we'll get to that. What about these questions? So do Pesor series converge? Not in general, right? I did not build in convergence. So these are just formal series. I start with formal Laurent series. So a Pesor series is simply a formal power series with rational exponents, where the set of exponents that you see has bounded denominator. No convergence. But of course, in our situation, we want these to converge. So these series actually converge. So under some mild hypotheses, the series that we get that represent the roots, they actually converge. So therefore, in here there is a subfield of convergent series. So there's a field of convergent series. So for example, converging near the origin or something like this, or converging in some region. So convergent series will form a subfield. The algebraic closure of K will be a subfield, right? K is a field whose scalars you can email. K bar is a field whose scalars you can email, whose scalars you can add and divide and multiply and subtract using univariate resultants. We practiced that. Okay? So K bar is a perfectly good field, right? And it sits in between. Right? So how do you do the series solution? So let me say a few words about this. Are there any questions? You're so quiet today. I promise it will get a little harder tomorrow. Okay? Okay, so how do you actually do this? So, okay. So for example, here's a test case. I think there's a nice example on page 7, x squared plus x minus t cubed equals 0. So how do you solve this for x? Okay? How do you solve this for x? Well, if you're a Korean middle school student, then you memorized a formula having to do with plus minus square root of something that writes x algebraically in t. Okay? That's one way to solve this. But you can take that expression and then do a series expansion into powers of t, right? So, but how do you directly, right? So maybe this 2 is a 5, right? To make that, how do you directly get the two series solutions? Okay, so we're going to practice that this afternoon. Oh, that's number 4. So yeah, the first problem, right? There's a nice equation you can practice this on. So. Okay, so what you do is this. You start by finding the u. So we want to first find, the first thing we're going to do is we're going to find the u. First we're going to find the u. Then we're going to find x0. That's the strategy. First going to find u, then we're going to find x0, and then iterate, and then iterate. Dot, 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 dot. Okay, so that's the algorithm. Okay, so first you find u0, the possible values of u0. For each value of u0, you find the corresponding values of x0. Then you replace your unknown x by x minus what you found. You make a new variable x tilde, right? And you do it again. And again, and again, and again, and again, and that's the algorithm. Okay? Now, when you should terminate and how far you should go, that's a problem of numerical analysis. But that's the basic algorithm. So let's talk a little bit about these two steps. First of all, how do you find u? And then how do you find x0? How do you find u? Okay, what happened to my equation? Let me write down the equation again. So here's the equation I want to solve. AD over t times x to the d plus 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 a1 of t x plus a0 of t is equal to 0. Okay, let me write down something. I want to take the minimum of val of ai plus I times u, where I is 0, 1, up to d. This minimum must be attained twice. Okay, so what does this mean? What is this? By val of ai, I mean the lowest power that you see in ai. So ai is a series in t. And by val, I simply mean the lowest exponent of t. So lowest exponent in t. The lowest exponent, right? Well, why is that? I claim that we form the minimum of these d plus 1 rational numbers. I make a list of d plus 1 rational numbers, and I look at them. And I claim that among these d plus 1 rational numbers in forming the minimum, there has to be a tie. Well, let's think about it. So suppose x is a solution, okay? Take this x and you plug it in. Plug in the x. Okay? So after you plugged in the x, so u is still unknown, right? Now you have an expression that depends on x. And it's 0. It's a series in t that's identically 0. Something, t to the something, plus something, t to the something. It's a series in t that's identically 0. But if a series in t is identically 0, the lowest term must be 0. Right? The lowest coefficient must be 0. But that means there has to be a tie. Right? The minimum has to be attained at least. So if I put in, x to the tu, the lowest term here has, here this has order valuation of ai. Then I plug in x0 t to the u, I get, d times u. And the ith term, I get, this is the order of the lowest term in t of the ith term. Is this clear? Yeah? So I look at ai times x to the I. I plug this in here. Then the exponent, the lowest exponent t, is this number. But there has to be a cancellation, right? There has to, in order for this to be a cancellation, the lowest power of t has to occur at least twice. Okay, so that's how I find u, right? So I look at, u is not known. This is a known rational number. That's an integer, right? So I simply solve this constraint. I find the values of u such that this minimum is attained twice. There might be several choices, but there's a finite list of choices, at most d of them. Maybe 2 or 3 or 4, and I find them all. Okay? But now, the second step, right? How do I find x0? Well, that's I have to solve a binomial system, right? Right, because now I have the lowest power of t, but then, here have higher order terms. Now there will be at least 2 terms. There has to be a tie, right? But here, this will be a binomial system in x0. Well, in this case, it's just a binomial equation. Typically, it's a binomial equation x0. Right? So now I have a leading coefficient. That leading coefficient depends on x0. You solve it. That gives you the possible x0 values. You plug in, and you iterate. That's it. That's Puiseux series. Okay. So let's practice this afternoon to solving Puiseux series. This is a built-in command in every computer algebra system. So in Maple, Magma, Mathematica, Sage, every major general computer algebra system has a built-in command using Puiseux. But I'd like you to sort of practice with this a little bit and get a feeling for it. How to write the roots in one variable. Now, once we understand that, we can come to 2 equations. So after we familiarize ourselves with solving 1 equation in 1 variable, then we're ready to looking at 2 equations in 2 variables. And I'll go over this tomorrow. So tomorrow morning, between 10 and maybe 11:30, 11:40, I need a little break, before the lunch lecture. So tomorrow morning, we're going to go back. Maybe a little bit this afternoon, we can discuss this. We're going to go back to this. And we ask the question, how to find possible pairs. Now we need pairs of lowest exponents, right? So now we need that's the first step. Right? So now we have 2 equations and 2 variables. Now we want to build series solutions, right? At start, coefficient times t to the u, blah, 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 for the x coordinate, and coefficient times t to the v, blah, 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 for the second coordinate. And that will involve drawing pictures in the plane, maybe drawing dual pictures, whatever. Okay? In any case, this will involve drawing red and blue pictures in the plane. But this afternoon, let's practice in 1 variable first. Okay? Okay, any questions? This is all I had to say this morning. Yes?
We know that the minimum obtains at least twice.
At least.
If it
At least.
For example, 3 times, then we have.
Then it's not a binomial system. Yeah, so that's correct. It will be, that is correct, at least 2 times. It will be attained at least 2 times. You're absolutely right. So in general, it will be attained at least 2 times. In the application, we can choose these exponents. And we choose them generically. And if we choose them generically, then it will be attained exactly twice. So we have some control. So we want to simplify the combinatorics, and we want to have them attained twice. So we can solve binomial systems. We can call the Hermite normal form subroutine, and it makes it simpler. Right? So if you can control the toric deformation, then you can make it exactly twice. But you're absolutely right. Absolutely right. Other questions? Yes?
So we discussed the binomial system. We had particular two polynomials, and we understood why the solution is the multiplication of degree. But what Bernstein's theorem says that for any pair of polynomials having the same Newton polygon, you have the...
Yes. So we will break this up. So
I wasn't sure whether...
yes, so this will be happening tomorrow. So we have this system, and we will break this into 3 binomial systems. We will reduce that for small values of t. This will break into 3 binomial systems. One having 2 roots, another one having 1 root, another one having 1 root. And there will be a red-blue diagram, or maybe it's dual diagram, that will tell us how to do that. Yes?
Is there some geometric interpretation of changing the vanishing sets of G and H?
What do you mean by change? Oh, I see. Well, the geometric and... well... so what happens as t goes from 1 to somewhere else?
Yes.
Yeah, I mean, they are finite sets, right? And they will change. I mean, this is a little bit, you know... so let me sort of draw the usual picture of numerical algebraic geometry. So here's t, right? And here's xy, right? So we're interested in t equals 1. And there will be a certain number of solutions, maybe 4. Okay? But of course, you know, now this is hard to get, so there will be some, you know, curves that go like this, you know, and maybe like that, you know. Somehow, you know, they might cross each other. So this is the real picture. Somehow, you know, maybe here there will be some, we want to analyze the situation for t equals this. This is the picture you have in mind, right? That's a yellow curve in 3-dimensional space with coordinates t, x, and y. Okay? That's the real picture. But of course, Matt never thinks about the real picture, right? Because in the real picture, we have the mixed discriminant, right? We have bad points, such as this one. We don't like these bad points, right? So what you do instead, you replace, so you get rid of these bad points by taking this t not on the real axis. So t goes from 1 to 0 or 0 to 1 via the complex plane, right? You walk around all the bad points. That clear? You don't take t on the real axis, because if you move t on the real axis, there'll be lots of bad things happen. But the number of bad things that happen in the complex plane is a finite number of bad points. You just pick a random arc in the complex plane, and then, you know, everything is fine. So if you do that, nothing bad happens, right? Everything is going to be okay. So the way we're going to do this, everything will be fine. Okay? So there'll be perfectly good branches. The only thing that's sort of delicate is, you know, this analysis. Is this clear? And for Reiner and other algebraists, okay, so for algebraic adults, right, this is the t-axis, so maybe this is the real numbers, but it's better to do this in the complex plane, right? So for algebraists, R is the valuation ring of a field with the valuation. This line is spec R. Spec R has 2 points. There's a generic point and a special point, and that's sort of the general theory. Okay? But in the application of numerically solving, we do this over the complex numbers, and then this down here is a little arc, a random arc in the complex plane that connects the complex number 1 close to the complex number 0. Okay, so that's enough for this morning. So I'll see you at 3 o'clock, and we'll practice Puiseux series and Newton polytopes and Minkowski sums and things like that. Okay.